This is a reminder that you should feel free to take as much time as you need to write all of the notes down and think about them. Pause the video at your own pace. Welcome everybody to section 4.5, day 2, graphing polynomial functions. We're going to tie what we learned about end behavior yesterday into what we're going to learn today about zeros, roots, intercept solutions, and all that in today, and as well as multiplicity. So, check it out. Here we're going to go. What we're doing is we're finding zeros of factored polynomial functions first. What does that mean? Well, zeros and roots, these are synonyms for each other. Kind of a big idea today is that these are very related to intercepts, which are very related to solutions. In fact, they're so related that students often mistake the difference between them. So let me show you what I mean. Here's a solution, here's an x-intercept, here's a zero or a root. And I've used the same polynomial here as here and here. If you were to say graph this function, f of x equals parentheses x minus 1 squared, you can see that the 1 is an x-intercept. That's because it's the location on the graph where it crosses the x-axis or touches the x-axis. 1, 0 means that 1 is an x-intercept. Similarly, if you were to solve this related equation, I took this x minus 1 squared and I just set it equal to 0, eliminating the f of x. It's no longer part of a function. It's just saying it's an equation that we have to solve. You can say that 1 is a solution. Here, 1 was an x-intercept because it's a location on a graph. Here, 1 is a solution because that's the value of x that you can solve for. Here, we're going to take this same function and we're just going to say that if you plug in 1 as an input, then the output is 0. That's what makes it a 0, or a root. So you can say 1 is a 0 in root because it's the input that produces 0 as an output. So when it's a solution, it's a value that solves the equation. When it's an x-intercept, it's a location on the graph that crosses the x-axis or touches the x-axis. And when it's a 0 or a root, it's an input that produces 0 as an output. They're all incredibly related. It's, the related function and the equation are constructed from each other. 1, 1, 1, it's all the same. Anyway, that's the big idea, that zeros and roots and intercepts and solutions are very related. Let's take an example. We're given a polynomial function like this, and we want to just test to see are 2 and negative 5 zeros? Well, I don't know. Why don't you just plug them in and find out? Is p of 2 equal to 0? No, it's not. Is p of negative 5 equal to 0? Yes, it is. You can see on the graph it also happens to be an x-intercept. Negative 5, 0, great. But if you plug in 2 as an input, you do not get 0 out as an output. It would not be required to graph this. All you really have to do is plug it into into this polynomial equation right here, polynomial function. Second example, let's find the zeros. So before we were testing, now we're going to find those zeros. Well, if you want to find the zeros of the function, what you could do is turn it into an equation and find the solution. So we're finding the solutions we're finding the zeros based on the solutions. Just solve it. You get x minus 2 is equal to 0, you get x equals 2, or x could equal negative 1. Those are the two solutions of the equation, and so therefore, since they're solutions, they also have to be zeros. These are going to be the inputs that produce 0 as an output. F of 2 is 0, f of negative 1 is 0, and they also happen to be x-intercepts. Here, negative 1 is an x-intercept, and 2 is an x-intercept. Find the zeros of g of x equals this crazy function. We got this right here. It's okay. We can just set it equal to 0 and solve. We've got here x minus 1 equal to 0, x plus 2 equal to 0. So we see that x equals 1 or x equals negative 2. These are both going to be x-intercepts because they are solutions to the equation. And therefore, since they're solutions to the equations, and since they're x-intercepts, they also are zeros of the function. G of negative 2 is 0, g of 1 is 0. Now, not only are they zeros of the function, but they also illustrate something we like to call multiplicity. And we're going to look at to establish the multiplicity of a 0, you look at the exponent. How many times is that 0 occurring as a 0? Like if you were to completely factor this out with no exponents, it would be x minus 1 written twice, 2 times, x minus 1 times x minus 1 times x plus 2 times x plus 2. We call that its multiplicity. That's the exponent on the factored form. This has a multiplicity of 2, and this has a multiplicity of 2. And it turns out that if the multiplicity is even, as they are here, then the graph is tangent to the x-axis. Notice here, at these zeros, it crosses, but here we can predict that it's going to be tangent. If the multiplicity is odd, then it's going to cross the x-axis, as they do here. Crosses, crosses, tangent, tangent, does not cross. And that's all it has to do with the multiplicities. So if you know the multiplicity of a 0, then you can figure out whether or not it's going to get across the x-axis or not. All right. Find the zeros of that crazy function by factoring. Well, we're going to factor it by grouping. So when you factor by grouping, you just take the greatest common factor of the first 2 terms. That happens to be x squared, and you're left with x minus 2 here. Take the greatest common factor of the second 2 terms, factor out a negative 9, you get x minus 2 here. And look, x minus 2 occurs twice. Since we have that happy coincidence, then we can just combine them both here. We have x squared minus 9. When you factor x squared minus 9 twice, you get x plus 3, x minus 3. So the 3 zeros are x equals negative 3, x equals 3, and x equals 2. So the zeros of the function are going to be identical to the solutions of the equation. These are solutions because they solve the equation, so therefore we can say that they are zeros of the function. When you plug them in as inputs, you get 0 as outputs. And because they're also zeros, they're also going to be, here they're also going to be X-intercepts. Notice negative 3, 2, and 3. They're color-coded here. Notice that they all cross the x-axis. That's because they have a multiplicity, an odd multiplicity, 1, 1, and 1. It's not written, but if you wanted to, you could say that there's an invisible 1 here, 1 here, and 1 here. You could write them out. Because their multiplicities are odd, they cross the x-axis. Do the same thing again here. Find the zeros of f of x equals x to the 4th plus 4x squared minus 45 by factoring. Well, I guess what I'm going to do is I'm going to say that we're going to do a u substitution. It looks very much like the format of something you could factor, except for the fact that the exponents are too high. So the related function could just be u squared plus 4u minus 45. You do factor x and you get this. Back substituting, it would be x squared minus 5, x squared plus 9 here. And we can say that the difference of 2 squares is going to be x plus square root of 5 and x minus the square root of 5. Here, since we're not going to be, you and I both know that imaginary numbers exist, but we're not going to deal with them right now. We're going to say that it could be, like a 0 of the function could be plus or minus 3i, but it's not going to show up on a real graph, a graph that can only show you the real values. So the square root of 5 and square root of positive and negative square root of 5s are where it crosses the x-axis. They're the zeros of the function because they are inputs that produce the zeros and output. And here, if you were to just use Desmos, I will say that it is kind of handy to be able to factor, because if you were to just use Desmos, you'd get these crazy long decimals, negative 2.236, and you'd think that was, you would wonder, like, why is it there? What's so interesting about 0.236? Why, but here you can actually get the exact values. Square root of 5 is a much, much better answer than negative 2.2 or positive 2.236, because this is rounded and this is not. So, that's that. Find the real zeros of f of x is equal to this crazy decimal thing. The instructions actually say using a graph. Well, they don't want you to try and factor this. You probably could. It would be incredibly difficult to factor. But anyway, using a graph, you just read it off, you plot it and use the graph, like the instructions tell you to. the zeros are going to be the same as the x-intercepts, and here they are. If you plug in negative 1.68 approximately, you should get this this x-intercept and this and 0. As an input, 2.154 is going to produce 0 as an output. I got that from here. You tell me what the remaining 0 is. So, kind of brings us to a question: why should we learn to graph without Desmos? Well, it's because if you can graph without Desmos, you really understand graphs in general. While we are learning, we want to make sure we do it without Desmos, and therefore we just get a whole lot more. I'm going to pull everything together. We're going to go equation table graph on this guy. The goal is to produce a graph here. And so we're going to pull in everything we've been learning together to eventually produce the graph. Here's what it looks like. Let's start off with end behavior. Negative 2x to the fourth has an even degree. 4 is even. Negative 2 is negative, so it's going to resemble the graph of negative x squared, which is down, down. And so the first thing you can do is just draw these arrows. You say it's down, down. The next thing we can do is we can say, let's find the x-intercepts. You can do that by solving the related equation. You set it equal to 0, ignore the h of x. Factor out x cubed, we get this and this. Notice that their multiplicities are both odd. This has a multiplicity of 3, and this solution has a multiplicity of 1. It occurs only one time. The exponent is 1. So we can say on the graph, we know we're going to have x-intercept of 0 and an x-intercept of, 1.5? Yeah, positive 1.5. And furthermore, we know we're going to be crossing the graph. So the end behavior says we're going to start out down here. We're going to cross at 0. We're going to cross at 1.5 and then continue down to negative infinity there. That's what we know without graphing it. We're going to make a table. And you can see that the x-intercepts are going to be on this table 0. This is what we calculated, 0 and 3/2 or 1.5. Those are the x-intercepts, the zeros of the function. And we record also over here that the multiplicity is 3 and 1, so they're going across the x-axis. It's always easy enough to also consider the y-intercept. Just plug in 0 to any function, and the value you get out is going to be the y-intercept. It happens to be that the y-intercept and the x-intercept are the same. The graph is going to cross through the origin. But it won't always cross through the origin, obviously. Plug in 0 to the function, you'll find out what the value is. That'll be the y-intercept, where it crosses the y-axis. And now, one thing you can do is you can take test points if you want. You can take values that are not going to be on the x-axis, but testing this region, and testing this region. We've got test points here. -1 will test this region, and we'll see that actually the point -1, -5 is down here. It's way down there. And so therefore we know that it's negative. We've further confirmed that it's negative. The test point 1 over here is right here, 1, 1. So we know it's going to be positive. And the test point 2 is going to be 2, -8 all the way down here, further confirming what we know about the end behavior. And if you don't like plugging in lots of numbers like if you don't want to calculate a whole lot, you just use Desmos to simplify the whole thing. You can define the function on Desmos and then make a table for getting an input-output table. Goes really fast that way. It's actually, these test points are not going to be 100% necessary because in this case, that we've got end behavior, x-intercept, and what you must cross. You've got end behavior here, and you must cross. So therefore, it's going to go like this. Anyway, connecting the dots, you've got what you need for a graph. And that's what these instructions say. So anyway, as Ronald Reagan would say, and Ronald Reagan is the audio check president for this video, I'd like you to start assignment 4E2, copy the problem list, and do the first problem. I'll see you in class.